Encryption is a process by which two parties can communicate with each other in such a way that if their communication gets intercepted, their message can't be read. And this is a process that may invoke images of spies in trench coats, sharing bomb codes with each other or something really high intrigue like that. But really, we all tend to benefit from encryption, most of us in our daily lives. A good example of this would be a credit card transaction, maybe buying something online where you need to send your credit card number and you want this to be done in a secure way. Another example is a web interface for your email or Facebook or something where you may notice that there's a little padlock symbol that appears up in the address bar of your browser. Anytime you see that little padlock symbol, your message is being scrambled up before it gets sent to the server, which descrambles it, and the same is true in the opposite direction. The server scrambles up its message before sending it to you, and then you descramble it. So how does your computer know how to unscramble and descramble these messages? Well, to go into the details of this, we're going to introduce a few characters to our story. So first we'll meet Alice. Alice wants to communicate securely with a guy named Bob, but they're going to want to do it via a public channel. What is a public channel? It's just some method for sending messages that could be intercepted by an adversary. The adversary, her name is Eve in this story. Eve likes to eavesdrop. Somebody who's tapped into your phone line or your internet connection can read all of the information flowing back and forth on that channel, which is why you want to encrypt it. Now, the best possible way for Alice and Bob to share a secret message is for them to meet ahead of time and share with one another a giant number called a secret key. If they both have the same secret key, Alice can, for instance, convert both her message and this number into big strings of ones and zeros called bits, and she can add them together bit by bit before sending the message. Remember, the secret key is just a string of bits that will look like a random assortment of ones and zeros, but Alice and Bob share the exact same string of bits. Now, after adding her message to the secret key, if Eve reads the scrambled message, she's going to see gibberish and won't know the secret key to subtract from this to get the plain text back. Bob, however, does have the secret key, and the first thing he'll do when he gets the encrypted message from Alice is subtract each bit of the key from each bit of the message, which will unscramble it for him and he can read it. So this sounds great, right? Both Alice and Bob now have a way of communicating with each other that's just as secret as the secrecy of the key that they shared before they started. Alice and Bob only need to keep Eve from being able to learn the secret key in order to be able to communicate without her being able to read it. But this scenario doesn't resemble very many real-world situations because the step where Alice and Bob generate and share this gigantic secret key had to happen in person before they were able to communicate securely over a public channel. That's called a private channel. They used a private channel to share their secret key with one another. You can think of Alice handing Bob a giant binder full of thousands of pages covered in ones and zeros. This is clearly not practical in most situations, such as when you want to make a credit card purchase from a person you don't know ahead of time. What Alice and Bob need, therefore, is a way to use a public channel to generate a shared secret key, and they don't know ahead of time if Eve is listening in on the public channel. This problem is addressed by something called quantum key distribution, which is a super cool way that Alice and Bob can use the wacky rules of quantum mechanics to generate a shared secret key. Quantum key distribution typically works by having Alice and Bob send little particles of light, called photons, to each other over the public channel, an optical fiber in this case. However, we want to be able to describe how this process works without going into the quantum physics of photons. So instead, what we're going to do is invent a little guy who's going to follow a set of rules, and he's going to mimic all of the physics of these photons. So we're going to have a box, and inside this box is going to be this little guy, this little homunculus living in there. In fact, there's an infinite supply of these boxes with an infinite number of homunculi living inside these boxes. The homunculus has a big paper map with him in the box, and it has the cardinal directions of the compass written on the map. If you've ever used a map inside an enclosed space, like a car, but particularly in a box, you know that it's awfully hard to unfold the whole map inside this enclosed space. So typically, what do? You fold the map in half or something and look at just the part that you care about. And the same is true for this little homunculus. What he actually does is look at half of the map and fold the rest up behind on the back. Now, this little homunculus guy is going to be fairly peculiar. He's got some very specific rules that he won't break, and this is how we mimic the behavior of a quantum particle. The rules that he follows are that he wants to be liberated from this terrible job of reading the map inside this box, so he's not very cooperative and he only does the bare minimum necessary. And once he accomplishes his task, he gets to open the box and run off into the woods or whatever and be happy with the other homunculi. So here are the things he can do. You can tell him to put a dot on the map in one of the 4 cardinal directions of the map. But a dot isn't very fun, so let's say it's a Waffle House. He's planning to build a Waffle House by putting this dot somewhere on this map. You can tell him to put a Waffle House on the west side of the map, for instance. And what he's going to do then is fold the map in such a way so that the part that's showing is just the west half of the map, and he puts a dot somewhere randomly on that map. You don't know where the Waffle House is other than it's somewhere on the west half of the map. Once he's drawn his Waffle House, he's only willing to do one more thing, and that is to answer a single yes or no question about the location of the Waffle House. The next person who asks him whether the Waffle House is on the north or south or east or west half of the map, he will answer either yes or no, but he's only going to answer one of those questions, then he's going to eat the map or something, destroy the map, and run off into the woods. Those are the rules of the homunculus. They're a little bit strange, but this is sort of the way that we're going to have our quantum photons work. So the way this process is going to work is that Alice is going to dip into her infinite supply of boxed homunculi and tell each one to put a Waffle House on this or that side of their maps, essentially at random. Bob is going to be receiving deliveries of these boxes of homunculi, and he's going to be asking each box questions about the locations of their Waffle Houses. So when Alice needs to send a box with a homunculus in it over the public channel, she's going to use the homunculus delivery service. This is our public channel. And this is a truck that's driven by this somewhat suspicious character named Eve, who's not necessarily to be trusted not to interfere with the communications. The best that Alice and Bob can do is to send the homunculus through Eve's service and try to tell if Eve has monkeyed with anything in the process by asking questions of the homunculus in the box. Once the two of them are done with this protocol, Bob is going to tell Alice which questions he asked of which box. He's not going to tell her which answer he got. The only thing Alice is going to tell Bob is whether he's going to throw out the answer or keep it. Each answer Bob keeps will end up being a bit in their secret key. Last, they're actually going to sacrifice part of their key to check to see if Eve was stealing their homunculus boxes, asking them questions about their Waffle Houses and replacing them with new phony ones that she tries to make copy the ones that Alice actually sent. So, for the first box, let's say Alice tells the first homunculus to put a Waffle House on the south side of the map. Eve picks up the box, and sometime later, a box is delivered to Bob. Let's say Eve doesn't interfere with anything for the moment. We'll go through the whole process later, assuming that Eve does. Bob picks a random compass direction and asks the homunculus, "Is the Waffle House on the south side?" And the homunculus says yes, because he looks at the map and there's definitely a dot there. Alice asks the next homunculus to put the Waffle House on the south side again, and the homunculus puts the Waffle House on the south side of the map at random. There's a 50-50 chance that this will be on the west side or the east side of the south half of the map. So Bob asks the homunculus, once it arrives, if the Waffle House is on the west side of the map. He gets a random answer from the homunculus this time because there's a 50-50 probability there. Let's say the homunculus says yes and then runs off into the woods. For the next one, Alice tells the homunculus to put the Waffle House on the west side. Bob is going to ask if it's on the east side. And when he does, he's guaranteed to get a certain answer. And the Waffle House is definitely not on the east side of the map, so the homunculus says no. For the next one, Alice tells the homunculus to put the Waffle House on the north side, say, and Bob asks, is the Waffle House on the north side? He gets a definite yes there. For the last one, Alice chooses north for the next location of the Waffle House. Let's say Bob asks it whether it's on the east side. He gets a no from the homunculus, who's equally likely to give a yes or a no for that one. Now, they would normally do this many, many times, thousands and thousands of times, but for the sake of brevity, we're going to stop right here with our minimal example. So now Bob calls Alice on the phone, again, a public channel, but maybe it goes off a satellite that goes through Eve's satellite company, and Eve can listen in on this part.
Alice, hi, this is Bob. I'm just calling to confirm our key code.
Alice tells him whether to keep the answer or throw the answer out.
Keep it.
Bob does not tell Alice the answer he got. Alice does not tell Bob which side of the map she told each homunculus to put the Waffle House on. So for the first box he received, Bob tells Alice that he asked it whether it was on the south side. Alice says, keep your answer, because she knows that he got a yes for that answer. For the next one, Bob says, I asked it whether the Waffle House was on the west side. Alice says, throw that answer out, because she has no idea which answer he got. It was 50-50 probability on that one. For the next one, Bob says east side. Alice says keep it, because she knows that he got a no for that answer. For the next one, Bob says north side. Alice says keep it, because she knows that Bob got a yes for that answer. For the last one, Bob says east side, and Alice says throw it out, because again, she doesn't know which answer he got. So at this point in the process, Alice knows that Bob got a yes for the first one, a no from the third one, and a yes from the fourth one. Therefore, they share a piece of secret information. This is their secret key. It's a 3-bit number, and you could say that the yeses are ones and the nos are zeros, or vice versa. But the point is that they now share the same information. Alice knows that this would be a 101, and Bob knows the same information, but they've never actually discussed that information over the public channel. Now let's imagine the same situation where Eve interferes with the homunculus boxes, and she takes each box and asks each homunculus where the Waffle House is, and then replaces the boxed homunculus with a new one of her own. Eve will intercept Alice's first box and ask the homunculus, is the Waffle House on, say, the south side? And in this case, she'll get a definite yes. That homunculus will then eat his map, jump out of the box, and run off into the woods. Then Eve will have to get her infinite supply of boxed homunculi. She'll tell one of them to put the Waffle House on the south side of the map, and in this case, no one knows what she did because Bob gets a definite yes for his answer, just like Eve did. For the second one, Eve decides to ask, is it on the west side? And in this case, there's a 50-50 probability that the homunculus says yes. And the homunculus unfolds the map, refolds it, he says yes, maybe he says no, let's say it's a yes. So then Eve gets a new homunculus because the other one ate the map and ran off into the woods. She tells this new one, put a Waffle House on the west side, and sends it off to Bob. When Bob asks it, is it on the west side, he again gets a yes, but it doesn't matter because they're going to throw that bit out anyway. For the third one, Eve is going to guess to ask it whether it's on the north side. The homunculus says, yeah, it's on the north side, but it was a 50-50 probability that he says this. When the homunculus unfolds the map and refolds it, maybe it is, maybe it isn't. So she grabs a fresh boxed homunculus and tells it to put the Waffle House on the north side. Bob asks, is it on the east side? And maybe this time he gets a yes. And that is very different from what he would get if Eve had never interfered with the message. For the next one, Eve is going to ask it whether it's on the west side. Let's say she gets a no from the homunculus. Eve will then get a new one, tell him to put the Waffle House on the east side, and Bob will say, is the Waffle House on the north side? We'll get a no from the homunculus because he asks, is the Waffle House on the north side? Eve guesses west on the next one. The homunculus gives her a yes. Bob asks, is it on the east side? And he's going to get a definite no in this case. So now Bob and Alice communicate over the phone over Eve's telecommunication network, and Bob says, for the first one I asked south, and Alice says keep it. And for the second one he says he guessed west, and Alice says throw it out, etc., just like last time. Now at this point, remember, Alice thinks that she has shared 101 with Bob. She thinks they both have that same secret key. The way that Alice and Bob determine that their communication has not been secure is that they decide to publicly reveal some of their shared bits, which they would clearly not include in their secret key later because they're sharing them over a public channel. Alice says,
why don't you give me the actual answers you got from the first and third homunculus box?
Because she already knows the questions. They're going to be throwing these bits out, and they're just going to use them to check the privacy of their homunculus delivery service. For the first one, I got a yes, and Alice says, cool. And he says, for the third one, I got a yes. Right then, Alice knows that somebody has tampered with their communication.
That Eve.
She told the homunculus to put the Waffle House on the west side of the map. Bob asked if it was on the east side, and the homunculus said yes. This is obviously wrong. So she tells Bob that their messages are being intercepted and that they need to try again.
We need to find a new delivery service.
Clearly, their public channel is not trustworthy. So this is how Alice and Bob can generate a shared secret key as long as no one is listening in. If somebody listens in, Alice and Bob find out about it, and they know that their message is no longer secure.